All right, another day, another start of the day, and yeah, welcome. Good morning. So today I will actually go from what we have done so far, what we have accomplished so far with the Silan-Boulez theorem, towards going back to the partitions, but now we will specialize those variables and get some weighted partition identities. I will explain like what I had in mind when I was doing these, and I needed to look at my own paper like yesterday for some time to understand what I had in mind. I mean, it just didn't make sense. So, but maybe that's what happens, like when you don't see your paper for like 6 years or something. Okay, but before that, Kant yesterday mentioned that there's this identity, q to the n squared minus n, z to the n, divided by q, q, n, and the z, q, n, for n, 0 to infinity. And this thing is 1 over z, q, sub infinity. And he proved it. This was one of the corollaries you get from the Heinz transformation, that you go to Gauss, Q Gauss sum, then down to this. And he said maybe Ali can prove it combinatorially, if he dares to. And I dare to because I will also need it. So it's perfect. And once again, as I did in the first lecture and everything, I will just plug in z being q first, just to see how things look, and reconstruct it, and hopefully prove this identity. Then I will try to reintroduce z. Okay, so z being q first. Z equals q. We have q to the n squared divided by q, q, n, and another q, q, n, so q, q, n squared. So n from 0 to infinity. And this is supposed to be q, q sub infinity. So on the right, we have a function that we have seen many times over the last 2 days. This is the generating function for all the partitions, right? Unrestricted partitions. So I gotta somehow construct all these partitions using the sum in some way. I will do it combinatorially. So to convince ourselves, without a doubt, that this is also the generating function for the number of partitions, right? And as I did before, I will just focus on what the sum end is first. I will try to construct a partition using that sum end with one specific, tag that I will keep, and then I will be summing over that tag, making it irrelevant. Okay, so the sum end. Q n squared divided by q, q sub n to the 2. So for arbitrary but fixed n. This q n squared, I want to make a shape out of it. When it was a qn, I just put them in a column of boxes, right? We did that too. When it was triangular numbers, we just put a triangle. So this is a square, so what type of shape should I make? I mean, we can go for like Rogers-Ramanujan type. We can just like do like 1 plus 3 plus 5. But I mean, I don't think it's going to help me this time. So this is squared. Let's stick with what the name says. So I will just say this is an n by n squared of n by n boxes, right? So this is a square of exactly n length. Now I end up with 2 of 1 over q, q n's. So let's focus on one of them. What was this? It was the generating function for number of partitions into the total number of parts being less than or equal to n, or the largest part being less than or equal to n. So over here, on this side, if I think that this is the generating function for partitions into less than or equal to n parts, I might as well put that partition, however that is, here, which has less than or equal to n parts. So if I were to merge them, which is like the next idea that I will have, if I were to merge them, this partition will never go below that corner, that vertex of the square, right? Because this exactly have n parts, this has less than or equal to n parts. Maybe it's going to come and touch that vertex, but it's never going to cross. Cool. So this was one of them. I have 2. Let me put the other one here. And again, this is a generating function for number of partitions. This time I will use that the parts are less than or equal to n. So that is a generating function for number of partitions where all the parts are less than or equal to n. So let me take one of those partitions and put it over here. And the largest part is less than or equal to 10. So if I were to merge them, if I were to just close this gap, now this corner is not going over that vertex of the square, right? So I fixed the size of the square. The size of the square is fixed. I can put something on the right-hand side of it, and I can put something below it, and these things don't cross. Like these are not growing my square, right? This is the largest square that is in this partition, starting from the top left corner. If there were to be a larger square, starting from the top left corner, it would have needed another box. Like here, but it can't have it because this guy is not crossing down, this guy is not crossing to the right. You see? So when I put it together, like, just think about merging it, does it still have that vague triangular shape? So when you combine it, this is also another partition, right? So we actually made up a partition by piecing out like 3 pieces. We fixed the largest square in our partition, starting from the top left corner. That was our fixed tagline. That was the thing that we're controlling. And then we put one partition right next to that, which has less than or equal to 10 parts, so it doesn't grow the square. And we put another partition below it. And that's what it is. So if you have any sort of partition, you can just say, oh yeah, which summand is this coming from? You would just go from the left-hand corner, look at the largest square that is inside of it, and say, oh, this looks like the n equals 3 case of that. So here, let's write it correctly. And these type of squares, the largest square that you can fit in a partition starting from the top left corner, are called Durfee squares. Durfee squares. So this guy, this summand, is the generating function for number of partitions with an n by n Durfee square. So the n is fixed. It fixes the size of the Durfee square. Then we put something below, something right next to it. We merge them. It becomes a partition again. There are no dents. We didn't create any dents. We didn't grow the square. So it's exactly known. Whenever given a partition, I can find which n it is coming from without a doubt. So this was one of the summands. If I were to sum over all of these possibilities, so inside I have the fixed Durfee square, like fixed size Durfee square, but I'm summing over like the Durfee size being 0, Durfee square size being 1, 1 by 1 Durfee squares, 2 by 2 Durfee squares. So I'm counting all of the partitions with any size Durfee squares. So I don't need to mention the size of the Durfee square anymore, right? Like over on the inside, the Durfee square size was fixed, but when I sum it over, it's just all of the sizes, possible sizes. So what I'm left with from this information is I have the generating function for the number of partitions for the summand. Well, cool. So we also saw that this is the generating function for the number of partitions. And we already knew this was the generating function for the number of partitions. So we actually proven this equality using combinatorics. Now, let's try to go back. Let's try to introduce the z, because this is what we proved is weaker than what is over here. Let's try to recover that variable z. What do you think it's going to count? What should the statistic on top of z count? It doesn't appear in one of the QPO hammers underneath, but it happens in one of them. And again, look at the summand itself. This n was the size of the Durfee square after all. And this z also comes with that n. So it's almost like I'm putting one z for each and every row once again. It's almost like it is counting the number of parts, right? For the Durfee square at least. The top portion for the Durfee square at least. And then I have a ZQ. Well, if I were to put it here, this would also be counting the number of parts for this partition. Right? And the other QQN, I will keep as a QQN. So this is not adding more parts, like count on the more parts, because they are already counted when I look at them row by row now. So Z, once again, here counts the number of parts. We needed to shift Z to ZQ to make the squared itself. But now, with that shift, I can introduce this Z here. And I would need to split these. ZQ, Q sub N. And over here, Z is counting the number of parts, where Z counts the number of parts. And we already saw this before. If you want to count the number of parts, you just need to introduce a Z here. And that's what it is, right? Instead of Z going Q, now I had Z goes to ZQ. So yeah. Now, these are equivalent, right? If you want to use this combinatorial proof to prove that guy, just take Z being Z over Q, and you get that time. Perfect. Thanks for the challenge, Khan. It was good, and I'm gonna need it in a second.
For future reference, I said if he cared, not if he dared.
And yes, I do care and I do dare, and it is proven now. Okay, let's remember Silem-Boulay's theorem that we proven yesterday, and let's move on from there. Boulay 06, I checked it yesterday. Yes, it was published in 06. It was on archive in 2003. It is Ramanujan Journal. And she has two generating functions. I wrote A, B, C, D in a row, but just to remember how things were, I'll put A, B, C, D as in a box. That's how we color the things, right? And this was the sum of partitions from all of the partitions, and we weight them with this number of A's, number of B's count. And it was this infinite product, minus A, B, C, plus Q sub infinity. I will recall what Q is. A, B, A, C, Q sub infinity. And this is let Q be the size of the box, so A, B, C, D. And then there's the parts in distinct partitions, A, B, C, D. This is partitions into distinct parts, weighted, and minus A, B, C. The top portion is the same as the previous case. And on the bottom, I don't have ACs and Qs. I have ABs sub infinity. Cool. So product representations, we have proven them. We proved this one combinatorially. Then we did the cancellation of repetition to get the next one. And we have already seen that if we were to plug in Q, the ordinary case, we end up getting 1 over Q infinity, which was the generating function for the number of parts, and Q. This is generating function for the into distinct parts, generating function for the number of partitions into distinct parts. Now let's try to do something more exotic, and that is what I have been called, what they were looking like when I first did that. Now you have freedom. I mean, you have a lot of freedom. You can plug in A, B, C, D, however you like.
May I ask a question? So
Please.
from this one, we can get the number of partition in odd part or even part, like with this definition.
So number of partitions of
Like the parts are odd.
all the parts are odd. I want to say not directly, but we can construct it. Yes, not necessarily directly, but we can definitely construct it. One thing that you can do is you can count the number of odd parts if you like. Let me show you that. Maybe that's a good warm up. Let's plug in P, QX, then q divided by x, then a qx, then q divided by x. Now what is happening? Just think about it. If you have qx, and followed by a q over x, whenever you reach an even number of boxes, starting from the starting of a row, whenever you reach an even point, the x's will cancel each other, right? So you won't see the contribution of an x. But if you were to end at an odd box, where you would get a qx, that is going to pop out an x. So this is the number of partitions in, like, you take partitions in all the partitions, and q is keeping the size. Again, I just refined everything. I just dropped down from A, B, C, D to the size q. But x is now counting the number of odd parts. X is number of odd parts. Why is that? Once again, if I stop at an odd position, so I put blocks of q, I put many blocks of q, and they have 2 by 2 size. So at the end of the block, I have an even contribution to my part size. If I stop at an odd position, though, if I get only a, for example, that will pop out an x. If I were to have the following b, it will cancel out, right? So that's why it is like, I mean, you can easily count the number of odd parts in your partition, for example. And this also shows that it's like somehow it is easier to count the number of odd parts. And it is much harder to count the number of even parts. I still don't know. I have formulas for this. We have formulas for this with the bound and everything. But somehow we just don't know how to count the number of even parts in a partition. Because if you look at Sillan-Boulez construction, or if you look at like this ABCD idea in general, we cannot count the number of parts. We couldn't include that z variable. We have A, B, C, and D, like 4 variables. We have a lot of freedom, but we don't have a count on the number of parts. Because one of the first operations that we did was take off these like long columns, which might change the number of parts. And we never even mentioned that, right? So it is hard to count the number of parts here, but it's easy to count the number of odd parts. So the difficulty comes from the even parts somehow. Yeah. And this is a good warm-up. So again, qx, q over x, qx, q over x. So if you stop at an odd position, you would end up counting the odd parts, number of odd parts, and q is the size and d. And if you end up at an even position, then x and following 1 over x would cancel each other. And you can go for other crazy combinations as well. I mean, I'm just saying crazy, but not really. You can just like take this being t and there being a 1 over t. So you can start counting now. Whenever I have a diagonal being of odd size, I will collect my t. When the diagonal has even size, I'm not going to collect anything. And so on and so forth. But I want to not introduce more variables. I want to drop down to see functions that we know, that we like, and maybe we will see some more connections. So actually what I want to do is the following. What if I plug in, let's say, q and q on the first row. So I count the odd indexed rows in an ordinary fashion, but I just don't even count the second, like even indexed rows. I just forget about them and put 1 and 1. So it is almost like you have the odd indexed row, you count it properly, then you have a ghost of an even indexed row, then you have the odd indexed row, which you count properly, then you have a ghost of an even indexed row, and you count the odd indexed row just properly, and you have a ghost, and so on and so forth. Right? When I plug in that, because I mean, again, in the fashion that I like to see that, when we're moving to the generating function, we are filling in our Ferris diagrams with these variables, and then we're multiplying them all together. So these even index rows have these ones, and in multiplication, they don't contribute anything. Now, what would that be? Let's see. We have the product representation coming from Silan. We might as well just plug this Q, 1, and 1, and see how it reduces. And this is just the algebra game now, or all the tricks that we have used before. So minus A would be minus Q, minus ABC would be minus Q squared, minus Q squared, and the full box, the Q is now Q times Q, the 1 times 1, it is Q squared, sub infinity. And underneath I would have AB, which is Q squared. I would have AC, which is Q times 1, so it is Q. I will have ABCD, which is Q to the power 2 again, and Q squared. Cool. This is something. We wouldn't reduce it to understand maybe this a little bit better. And on the top, I have distinct parts, 1 modulo 2 and 2 modulo 2. Right? So I have all the parts that I start from 1, go in steps of 2. I start at 2, go in steps of 2. So I actually have all the parts over there. Like all the numbers are going to either be odd 1 modulo 2 or 2 modulo 2. So this is negative Q1, Q1, sub infinity. I have the same thing underneath. I have Q to the 1, Q to the 2 with Q squared. This one is just like that, negatives are not there, but the idea is the same. So I have Q sub infinity. But I still have a Q squared infinity. Right? Recall we did this yesterday too. So if I have Q2A, or Q4, like Q2B, sub infinity, you can split it into 2 pieces. That's like evens. You can have QA, QB, sub infinity, and minus QA, QB, sub infinity. And it was coming from, that's 1 minus x squared is 1 minus x and 1 plus x. Right? We just open these up. In each and every parenthesis, we just split them, and regroup. I can do that here. I have Q squared here. So let's split that one. I have minus Q sub infinity, Q sub infinity, and it is Q sub infinity and minus Q sub infinity. So things cancel from top and the bottom, right? And finally, we reach a point where we cannot cancel anymore. So I have a Q infinity, another Q infinity, so it is Q infinity to the power 2. This is not a generating function that we have seen before, but we can make up our minds about it. It looks like the ordinary generating function, 1 over Q infinity, but I have 2 copies of that. So this looks like 2 copies of the generating function for the number of ordinary partitions. Maybe I should change that word 2 copies and put it somewhere else. This is the generating function for the number of partitions where you have 2 copies of partitions. So you have a pair of partitions, or a partition in 2 colors, if you will, where some of them are green, some of them are red, and that's coming in 2 colors. I'll write in a better way, but when you plug in QQ and 1, it is a generating function for partitions into 2 colors, or a pair of partitions. Some coming from the first 1 over QQ infinity, the second part is coming from the other QQ infinity. Cool. Let's do the same thing for the distinct parts. Not a crazy idea, right? It's just we're plugging in values, we're seeing like how the generating functions look, we're trying to understand them. And we didn't see anything mind-blowing yet, or maybe we are never going to see it. Hopefully we will. Minus Q squared sub infinity divided by, I have AB Q infinity, which is Q squared sub infinity. And I will do the same trick, minus q minus q squared. Q squared is the whole negative q sub infinity divided by q squared infinity. I will do the same trick once again to cancel things. It is q infinity minus q infinity, and they cancel out 1 over q infinity. Ah, good. This is something that we know. This is something that we have seen before, right? I think this is a time to like perk up and say like, I know what this generating function counts. This is the number of partitions into distinct, this is the number of partitions, period. That is just what it was. But however, it was associated with phi, the number of partitions for the ordinary set of partitions. Now I got that associated with partitions into distinct parts somehow. You see, we started with partitions in distinct parts. We decided to ignore every second row, and the total count turned out to be the total count of number of partitions. How's that? How does that work out? Well, that was interesting to me in 2016. That apparently was interesting to other people before me, but I didn't know when I first saw this. Let's see what we did again. Given a partition pi, which is lambda 1, lambda 2, lambda 3, so on and so forth. Let's remember that the size of pi was the sum of these things. Now I will define an O of pi, which is the sum of the odd elements, like odd indexed elements. So lambda 1 plus lambda 3 plus lambda 5. So I'm ignoring every second part. Then, in this notation, I take partitions from the set of partitions into distinct parts. I'm taking partitions from the set of partitions into distinct parts. I am changing the statistic from the size of the partition to the sum of the odd parts of the partition, because I'm ignoring every second part. I don't care about what is happening at lambda 2. I don't care about what is happening at lambda 4. And this turns out to be this 1 over q infinity, which is the generating function for number of partitions coming from the set of partitions where I count things with the ordinary size. So somehow I change the statistic in the exponent, and they count the same amount. Interesting, right? Apparently, in 1997, Schmidt suggested this problem in American Mathematical Monthly. American Mathematical Monthly is a nice journal. They publish some articles and some more general reading, plus some problems. And the problems are the things that people just suggest that they know the answer to, but it's cute, they find it cute, so they send it as a problem for other people to solve as well, and people get some ideas from that. So in 97, Schmidt had this result. He sent it to American Mathematical Monthly, then 99 it got published. Mork proved it in 99 issue. Then other people proved it. In 2016, I proved it. 2018, it got published. Last year, Andrews and Paule proved it. And overnight, this became an instant hit. So let's write it in a combinatorial version, in some combinatorics words. Let's see what we're counting, and let's attribute this to Schmidt. So this is Schmidt's problem. The number of partitions into distinct parts whose odd indexed parts sum is equal to n is equal to the number of partitions of n. Cool, right? The interesting thing is, yeah. So, oh yeah, and this is, again, as I said, 97 submitted, 99 American Mathematical Monthly. And more proved it, other people proved it as well. Complete different methods. This is yet another different method. And yeah. Well, but we changed something really fundamental to what we have said so far. We were always counting the partitions with their sizes. We were grouping them with their sizes. That was how we constructed the generating function. But now we changed the fundamental statistic. So the question is, can we change this fundamental statistic to anything that we like? Can I do like 1, 1, and Q, for example? Can I ignore the odd index parts? Why not? Right? Let's try doing that. If I, apologies, well, I ate some chalk. And I'm still like, eating chalk. So that's, yeah, something to avoid. Yeah, let's try to plug in 1, 1, and QQ and see directly that it's going to fail. So if I were to plug in 1, 1, and QQ, I will have -1. So it's 1, 1, QQ is my assignment. -1, then over here, -1, -1, 1, Q, so negative Q. And then 1, 1, QQ is Q squared. And underneath it is 1 base Q squared, sub infinity. And you would directly see that that first one is a pole. Just remember the cupola hammer symbol, that it's the start thing, so it is 1 minus that first thing. You directly introduce the pole in your function because of that one. So it's a no-go. We cannot have a 1, 1, at least on the top row. It is not going to work out. Because think about it. If I forget about the top row, I don't know how large it is, then I would be counting like infinitely many partitions with larger and larger top rows. And you can just pick the second part to be 1, and you can get the first part as large as you like, so you will be counting infinitely many partitions from that count. So yeah, I need to have some contribution coming from the odd index rows, or at least from the top row, for this to make sense. So I cannot just ignore anything. That's one limitation. And yeah, but other than that, everything seems to be working out. And yeah, let's visit this first one again. So this one, the second one was Schmidt's problem, written in another language. What about this first one? We proved it quite easily as well. And that was not known in literature, actually, in 2018, like before I found it. And turns out it is that you count the number of partitions, not into distinct parts, you count the number of partitions where the odd indexed part sum is equal to n, and that is equal to number of partitions into 2 colors, into pairs, right? Perfect. So this theorem, I'll say, yeah, doesn't matter, so it's the number of partitions where the odd indexed parts sum is n is equal to number of partitions of n into 2 colors. I will do the coloring in some fashion soon enough, but in 2 colors, meaning that, I mean, I have 2 copies of it. You can just split them. You can put the green parts and the red parts, partitions in two baskets, and you would have 2 copies of partitions. So this one was in this paper of mine in 2018, both of them. Not attributed to Schmidt, so apologies to him. I didn't know. And later on in 2021, Andrews and Pauli also found this theorem. And they later also apologized. Like, they didn't know that I proved this one either. And they're really gracious that they also said that they didn't know. But I mean, if you attach the names Andrews and Pauli to anything, it becomes an instant hit. So this theorem also became an instant hit. People started calling it the Andrews-Paula theorem, and I'm like, oh my god, no, no, please don't. And yeah, so I'm trying to call this like Uncu Andrews-Paula theorem. So a number of partitions where the odd index part sum is equal to n is equal to the number of partitions of n into 2 colors. So let's try to see these colors a little bit better maybe. And yeah, I have about 10-15 minutes. Or try to go from this unconventional statistic, big O of pi, to the conventional statistic of size. Let's try to translate this idea here to where the statistic is pi. And this is what I was suggested. When I wrote the paper, they said, like, well, this seems a little bit exotic. Is there a way you can translate that back to the size of partitions where we like to see things? So can I find a way of seeing that this is something where I'm counting the size of partitions? Maybe change the sets, most definitely. Maybe change something else, most definitely. How can I translate this side to something else? All right. And I did. Turns out that theorem was also in the literature. And I found that. Let's do that now. So the question is, this big O is looking so exotic, can we move to a size statistic? Would it be possible? Let's think about it. I take partitions into distinct parts. So every part differs a little bit. Every part has a gap of 1. Then I ignore every second part. So only the parts that count now. So I have this part, then I have shed of a part. And the gap here is at least 1. Then I have another part, but this is in distinct, like this partition is in distinct parts, so there's at least a gap of 1 again. And I have a shed of a part, at least 1 again, the gap. And yep, another 1, and gaps again 1. So I ignore this, I do that. If I decide to count only the parts, if I decide to focus on the parts that only, the ones that count towards my generating function, the gaps from the one that counts to the next one that counts is at least 2 now. So there needed to be 1 gap to the next part, which I ignored. Then from that ignored part to the next one, the gap needed to be at least 1 once again. So combined, the gap needs to be at least 2. Right? Does it remind you of something? So let's define a set of partitions. Let RR1 be the set of partitions. This time it's a set for me where the difference, the gap difference between parts is greater or equal than 2. So it seems when I'm trying to change this big O statistic into the size of parts, so if I only want to focus on the parts that count, like the boxes in these white rectangles, I'm dealing with partitions that is usually counted by the gap conditions of Rajussomanjan identity. However, I need to be a little bit more careful. So yeah, from this pi in D Q big O of pi, I move to the Rajussomanjan. I understand that if I want that size over here, I need to go to the Rajussomanjan 1, but it feels somehow off. Because I cannot really say that the number of Rajussomanjan partitions is equal to the number of partitions. It's not true. So what am I missing? So what is going on? Maybe there's some wiggle room that gives me somehow the same answer, same images for this Rajussomanjan partitions that I'm not seeing yet. Let's think about that. If this first row that counts for me is quite large, and the second row, I mean, from like the first and the third, there's some gap, sizable gap. The second row that I'm gonna ignore might be anywhere from like this 1 gap to 2 gaps, to 3 gaps, to 4 gaps, to 5 gaps, whatever that is. It can have many different values, but I'm going to ignore them anyway at the end, right? For the statistic, for the odd index part sum. But if I want the sum, it feels that I should be counting all of them because those are the things that I ignored, and that is where those ignored parts could have showed up. So the difference becomes here. We were always counting partitions with ones. So one of that, all that. But here, it is not one anymore. So this is the image of a map, of a surjective map, from partitions to distinct parts to Rogers-Mongeon partitions. And now there's a weight on this partition, which I will later call 1, 2. So what do you think that weight is supposed to be? I think we can figure it out, right? So how many possibilities are in between lambda 1 and lambda 3? So the original portion, it was a partition into distinct parts. So whatever is in the middle, that lambda 2 cannot be equal to lambda 1. It cannot be equal to lambda 3. Right? So the gap of 2 from lambda 1 to lambda 3. But now I'm thinking, how many possibilities are there for lambda 2? So that I would put it as the weight. That there are that many pre-images of this Rogers-Mongeon partition. And it's not too bad. So yeah, think about just a concrete example. Let's do a concrete example. 1, 2, 3, 4, 4, 5, 6. And this is 1 box. So I have 6, I have 1. This is the image after I ignore the second part. It could have been 6, 2, and 1. It's a partition of distinct parts. It could have been 6, 3, and 1. It could have been 6, 4, and 1. It could have been 6, 5, and 1. So all of these partitions, 6, 2, 1, 6, 3, 1, 6, 4, 1, 6, 5, 1, actually gets mapped to 6 and 1 under this sum of all the index parts.
Like lambda 1 minus lambda 3 minus 1.
Exactly. So in between these, I know I need to occupy one of the boxes anyway. There are lambda 1 minus lambda 3 boxes here. I need to occupy at least one of them. And yeah, I just need to make sure that how much more boxes can I occupy, and that is the lambda 1 minus lambda 3 minus 1. So this omega, if I were to call this pi to be lambda 1 prime, lambda 2 prime, so on and so forth, this omega pi is starting with lambda 1 minus lambda 2 prime minus 1. From lambda 2 to lambda 3, from lambda 2 prime to lambda 3 prime, it will be again the difference minus 1 of lambda 2 prime, lambda 3 prime minus 1, and it will go this way. Lambda k minus 1 prime minus lambda k prime minus 1. So it's always just how many pieces could have been in between. Till we reach the last point. So we reach the last point. Maybe it was of size like 2. Now here it is the issue that I don't know if there was a part underneath. Because this was an odd index part. Maybe there was an even index part that I ignored. Maybe there wasn't an even index part that I ignored. Right? So there's an extra possibility that maybe there was no part at all underneath. So it just becomes, if lambda k is the last part, I would have lambda k and lambda k minus 1 parts. Is it correct? Or lambda k plus 1? So if 2 is my last part, there's like something larger, maybe there was nothing under this, or maybe there was just that one box. If it is 3, maybe there was nothing under this, maybe there was one box, maybe there were 2 boxes. So yeah, the last one is just the last point, lambda k. So the weight turns out to be a multiplicative weight You can see I'm multiplying a lot of different possibilities. And that is written as, so number of partitions pi minus 1, I from 1, and it's lambda I minus lambda I plus 1 minus 1. Those are the intermediate possibilities, the number of possibilities times lambda, where the number of parts are pi. So the n times the last pi. Well, isn't that cool? So we are counting a subset of partitions, a refined subset, Rogers-Monjan partitions, where the gaps are at least 2, with some weights, and at total, when you trace it back to our original theorem, it counts the number of all the partitions. So this is still true, that this is equal to number of all the partitions, pi in P. So yeah, this one was Schmidt's theorem. This translation, I think I did it first in the 2018 paper, but this connection was also, so from the long way I proved that, but from the short way, this was also proven by Alladi in 2019. So Krishna Alladi from my alma mater, University of Florida, also proved this weighted identity in 1997. Not 2097, 1997. So you take Rogers-Monjan partitions, which is a really small subset of all the partitions. You put a multiplicative weight on it, and turns out you're counting the whole set of partitions. And he has some dreams, I have some dreams. His dream is to see a set relation just like this one. His dream is to see a relation where this is not Rogers-Monjan 1, but this is the partitions from distinct parts. So he wants to count the number of partitions from distinct parts with some weights and get the count of all the partitions instead of the Rogers-Monjan. There's an obvious one. But he doesn't want an obvious one. He doesn't want a trivial one, just another more complicated one. And for me, I would be more interested in seeing more relations where you change the statistic, where you change the weight, and see what type of different connections we can get with different statistics. And I think we can talk about some things that we can do with that like next time. Okay? All right, thank you.